In this video, we're going to talk about scientific notation and significant figures in chemistry. So what is scientific notation? Scientific notation is a useful thing that we usually use to see really big or really small numbers easily. So for example, what I mean by that is take the speed of light. So the speed of light is 3,000,000,000 meters per second. That's a really big number, right? That's a lot of zeros, so it's a lot easier for us to write that number as 3 times 10 to the 8, indicating that there's 1, 2, 3, 4, 5, 6, 7, 8 zeros in that number, i.e. it's 3 times 10 times 10 times 10, 8 of those 10s, and so on and so forth. So that makes writing numbers, really big numbers or really small numbers, very easily, especially when it comes to things like electrons and protons and neutrons, because those are itsy bitsy tiny. The mass of an electron, I'm not sure of the number, but I feel like it's to the minus 16 or something like that. Here, let me see really quick. Okay, so I was way off. The mass of an electron is actually 9.1 times 10 to the minus 31 kilograms. That's a tiny number. So if I had to write this out with all the zeros, it'd be 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 31 of those zeros, and then the 9 and the 1. That's a lot of zeros. It takes a lot of time that we don't have. So instead, we use scientific notation to denote these really small numbers that we often use in chemistry, or really big numbers. Let's take a look at how to do this. So here's an example. We've got our 10,000 micrograms per meters cubed. Micrograms is a mass. Meters cubed is similar to centimeters cubed, i.e. it's a volume. So this is a density here, mass, volume. So another way to write this is times 10 to the 4. So essentially how we can kind of think about this is whenever we have something that's raised to a positive number, so like a plus 4, we can take our decimal place in our 10,000 right here and move it to the left by 4 spaces. So 1, 2, 3, 4 hops this time. And then if we have a smaller number, like 0.001, our exponent on the 10 is to the minus 4. We're going to go the other way. So that means that for 0.0001, we're going to have 4 hops to the other direction. 1, 2, 3, 4. Right? In order to give us 1 times 10 to the minus 4. This is 1 times 10 to the 4. So the difference here is when you have a negative exponent like this one, this is a really small number. So it will be less than 1 or whatever value is here. So if this is like 9.0, it'll be less than 9. It'll be smaller. So you'll add zeros in front here. Whereas the other one, if you have a positive number like this one, it means it's a really big number. So we're going to add zeros after this digit that's indicated here. That's scientific notation. Let me give you some practice with this. Okay, so try this one on your own. See if you can convert these numbers into scientific notation using the method that I just showed you. Let's take a look at how to answer this one. So 1,000.0 is a bigger number, which means that our exponent will be positive. Positive exponent. So this number here is 1.0 times 10 to the 1, 2, 3 hops. 10 to the 3, i.e. 1.0 times 10 times 10 times 10. If you put that in your calculator, you end up with 1,000. That's what we're saying here, 1,000.0. Let's do the next one. 0.0042 centimeters into scientific notation. This is a small number, meaning we're going to have a negative exponent here whenever we do scientific notation. So we're going to move our decimal place 1, 2, 3 hops. So that gives us 4.2 times 10 to the negative 3, because this is a small number. So what that means is essentially we've got 4.2. Instead of multiplying it by 10, we divide it by 10 each time. So divided by 10 times 10 times 10, which means we've divided by 1,000, which gives us this number here. So the correct answer to this problem is 1.0 times 10 to the 3 and 4.2 times 10 to the minus 3. Now the next thing you're going to learn in this video is about significant figures. Significant figures, we have some rules in order to determine them. Significant figures are numbers that include all digits that are known with certainty, like you know exactly what they are. And then there's a digit at the end of your number that is uncertain. So let me show you what I mean here. So that might be a little confusing to understand. So all measurements contain uncertainty because sometimes we can't measure things exactly. Like maybe the scale that I use can tell me that this Apple Pencil here is half, maybe it's like 1 gram, right? I think it's a little heavier than that. It's probably about like 3 grams. So it might tell me that it's 3.0 grams. But this pencil here could be 3.007 grams. I just don't know that because my measurement device only measures it to 3.0. So there could be other digits there that I don't know what they are, meaning those are uncertain. The only ones that I know for sure exist are the 3.0. I don't know that beyond that 0, there's other digits. I can't determine that using the measurement device that I have. So that is kind of like this example here. This measurement device, if you look, it has 2 decimal places on it. So it can tell you that this one, it knows this value, it knows this value, and it knows this value, but it doesn't know what comes after that value. So say that it was 0.001, and the next digit was a 1. If you rounded this value, you get to 0.11, same number, right? Now let's say that instead, this number is 0.19. It doesn't know that. The scale cannot read that number. But if you were to round that number, instead of the 0.01, be 0.02. So that's what this is meant by it's uncertain. Because it could be 1, it could be a 9, it just can't read it. So it doesn't know what is best to round to, essentially. So that's that uncertain digit that it just doesn't know. Same here with this balance. So this balance is more accurate. It's better at getting the number because what you can see is that it's got 1, 2, 3 zeros here that it can determine accurately. So this balance, it could read this number. It could tell you for certain what that number is. But this one here, it's not going to be able to. That's kind of what we mean by what's significant and what's not significant. Okay. Now, when you see a number written down, we have to make measurements in chemistry, and we have to record those measurements. When you see a number written down, the number that is recorded is how many digits this scientist or person or student, or whoever is making the measurement, could actually read to. So it's something they know for certain. So if you have a non-zero number or integer, it means it's always significant. So like this has 1, 2, 3, 4 significant figures in it because they're all non-zero numbers. Same with this one, 1, 2, 3. This person knew these 3 numbers for certain, 3 sig figs. Okay. There are certain zeros that are not significant. So all numbers that are non-zero are significant. Things that are zeros, sometimes they're significant, sometimes they're not. So I'm going to teach you the rules behind these. So if you have a 0 in front of your number, like this 0.0392, these don't really matter here. These are the values that are considered significant. So this one would have 3 sig figs. Here as well, 1, 2, 3, 4, 5, 6. These don't really matter. Here we're saying we have 4 sig figs. However, things that come after your non-zero numbers, i.e. trailing zeros, do, because that means that you've read all of those exactly. So if you have 37,3700 and a decimal place, that means that you know these zeros for certain. Like you were able to ascertain those. Those were not a 1, they were not a 2, they were not a 3, they were not any other number but 0. So this has 4 sig figs on it. Same with this number here. This 0 that's after the decimal place, I wanted to show you an example where the 0 is before the decimal and an example where the 0 is after the decimal. But what you can see is this is a trailing 0. It comes after your number. So this one has 5 sig figs because we've got 1, 2, 3, 4, 5 numbers. 3 of those are trailing zeros. So 5 sig figs. Okay, so these are not significant. And these, are significant. Okay, this is significant. I saw my mistake here. I instinctively added a 0. So this number here, 3,700, these zeros are not significant unless there's a decimal place that indicates that they were ascertained. So that decimal place says we read up to those 4 zeros. We didn't just read 3,700 and then stop and approximate. So I instinctively added a decimal place here because that makes these significant. Now they're significant because they're wedged in between a decimal place. So you can put this point here without a 0 after it. If you did this, 0.0, this is 5 sig figs, whereas this is 4 sig figs. So know that difference here, and this is only 2 sig figs because there's no decimal. So we can't know for certain if those zeros were read with certainty. That's what makes these numbers different. Let's take a look at captive zeros, okay? So captive zeros means they're zeros in between significant numbers. So if they're in between something that's a non-zero, all of those count. So an example here is the 16.07. This is 4 sig figs because your zeros are in between 2 significant figures. Here, this would be 5 because they're in between 2 numbers. A captive zero can also be made captive by adding a decimal place. So 16, so I showed you that here. So these we would consider captive zeros because they're in between a significant number and a decimal place. That's another way to make these. Okay. So ignore that example. I think this demonstrates that concept just fine. As well here, these are captive zeros because they're in between a significant number and another significant number. This is significant because of this rule here, because it's a trailing 0. So here's a review of the significant figure rules that we learned. So what is a sig fig? Here's your definition here. It includes all digits that are known with certainty plus 1 digit that's not certain. So in order to determine if something's a sig fig, you can look and see if it's non-zero. If it's non-zero, it's always significant. That one's an easy rule. Now, if you see a 0, that's where it gets a little hairy. If it's a leading 0, if it comes before the number, it's not important. If it comes after the number, it's a trailing 0, it matters. And that is usually after the decimal point as well. So if it's like a 3700, these aren't considered trailing zeros. But if it's 3700, That's a trailing zero because it's after the decimal point. So do be careful there. That's a trailing zero. So this will come after the decimal. And then captive zeros also matter. So that's these in here stuck between something significant. Or say you had 207. That's a captive. It's in between two significant figures. So that one matters. All right, and we're going to ignore this one. Okay, so that's how you determine if a zero matters or not in measurements. And all non-zero integers are significant, so that one should be easy to remember. So give this a try and apply your knowledge on this quiz here. See if you can figure out how many sig figs are in each of these numbers. Let's take a look at how to answer this one. So for A, we need to determine if our zeros are significant or not. All non-zero numbers are always significant, so we always know that those matter, but we've got to figure out if our zeros do or not. So we need to determine, is this a leading zero, a trailing zero, or a captive zero? If we look, these are leading. They come before the number. They don't matter. This is trailing. So it does matter. So that means it's significant. So we have 4 significant figures for this one. 100 pounds. All non-zero are significant, so the 1 is obviously significant. There's no decimal place here. So you might think these are trailing zeros, but because there's no decimal place, we can't determine that. So this would just have 1 significant figure. If we wanted to make the zeros significant, we could write this 100 pounds number by including a decimal place. And then we know for certain that those zeros were measured with accuracy. And that would give us 3 sig figs. So make sure that you understand that distinction there. Let's look at 101.05. Non-zeros are always significant. We know that. Let's take our other zeros and determine leading, trailing, captive. In this case, they're captive. They're stuck in between 2 significant figures. So that makes these important as well. Captive zeros. Captives. All right. And then our last one, these are important because they're not zeros. Let's take a look at our zeros. This one's trailing because it's after the decimal point and it's after the number. And this one is captive because it's between a significant zero, we've determined that one's significant because it's trailing, and another significant number here. So that gives us that all of these matter. So this is 4 significant figures to answer this one. You'll have more practice problems on your homework. Let me know if you have any questions about this.